This is class number 4 in firing of ceramics. This is a revised class. I have corrected some of the things in this class, so I hope that this is the one that you're looking at. Now, we're going to have 3 classes, including today's, which is going to look at specific types of ceramics to be fired. The whole purpose of this is to show you that there's a correlation between things happening within the ceramic and things that you must do in firing the ceramic, particularly with respect to adjusting the firing schedule, meaning the heating rate or cooling rate. It's fairly obvious to everyone that the dwell at high temperature, the soak time, as we call it in the kiln, is required to achieve uniformity within the kiln load. And that soak time is adjusted so that you can meet your physical property goals, particularly with respect to porosity and strength when the ceramic is fired. But nevertheless, we can cause defects in the ceramic by heating too fast during certain periods or cooling too fast. And so I have 3 classes to illustrate those points. The first one is today and talking about heavy clay products, earthenware products. So if you don't make these kind of products, if this is not your primary interest, I urge you to take a look at this class and think about these correlations between internal changes and the quality of the ceramic that you produce. Just for a little review, we have previously talked about phase equilibria, and in these classes we've talked a bit about we have an overall composition in a phase equilibrium diagram. This was an example about the lime magnesia silica phase diagram. So we've made a final composition, which is up here. It looks like it's a bit over 90% MgO in the composition. So we're making a magnesium silicate ceramic. On heating up, however, we added calcium oxide as a flux to aid us in sintering, a sintering aid. And the calcium oxide worked by creating a first liquid at a lower temperature than the solidus temperature, the temperature of melting of the final composition, which up here you can estimate it, it's around 1485 degrees Celsius, the melting point of some of the phases in the compatibility triangle. But nevertheless, when we use lime as a flux, the first liquid occurs at about 1320 to 1370 degrees Celsius. So there is a formation of melted phase within the product on preheating. When you're heating up at about 1320, it can be lower than that with alkalis present. I understand that. It's dependent on the overall composition. But within the fine area of particles of the composition, we're going to form some liquid. Now that liquid is not an equilibrium phase, so the composition of that liquid must go toward the final composition of the ceramic. So the composition of that liquid is going to change. It's a non-equilibrium liquid, and we call it a transient liquid. It's a transient liquid because it disappears in time during the firing process, but it aids us in sintering and densification. Now, in laboratories, of course, I've talked about some of the analytical equipment that we use. We use differential scanning calorimeters. Now, this is the original Netsch instrument that I bought. It was a wonderful instrument. It's since been replaced in my laboratory. But nevertheless, a specimen is suspended on a specimen platform here. The furnace is brought down over the top of the specimen. And so we can measure thermogravimetric analysis on heating. TG, gravimetric analysis, that's the weight change on heating. We also can measure energy flow by comparing what's happening within the specimen to specimens of inert material. And we can determine if energy is flowing into the ceramic, an endothermic reaction, or if the ceramic powder is evolving heat, an exothermic reaction. So we get two very important things here: weight change versus temperature, and we can tell and quantify endothermic and exothermic reactions. Now, in this particular estimate, the gases that are evolved are coupled to an infrared spectroscopy instrument, and that allows us to identify a lot of evolved species that result from the heating process. For example, carbon dioxide, when we oxidize the carbon or binder, if it's a carbonaceous binder in the material. So we get a lot of information. Now this laboratory instrument has been replaced with one that's coupled to a mass spectrometer, which allows us to quantify some different things, but nevertheless, this was a wonderful instrument. Here is a sample of a simultaneous thermal analysis curve on heating material. This is kaolin. The left axis here is Tg as a percentage. Here's the starting weight up here. The green line is the Tg curve on heating. So we're starting at 100%, and you can see that we're going to lose some weight as we heat, with an inflection point starting up here around 800 degrees Celsius or thereabouts. Excuse me, 800 degrees Fahrenheit or thereabouts. It's a constant problem for me to keep up with degrees Celsius and degrees Fahrenheit in these types of reactions. But there is a reaction occurring here which results in a weight loss. Now, if you look on the DSC graph, that's the axis right here, and we're going to see that there is a reaction that takes place. Excuse me, this is the blue line. Reaction that takes place right here. It's an endothermic reaction, and we get a peak at 1024 degrees Fahrenheit. In this case, an endothermic reaction. We can tell the direction of the reaction using the little key right here. Exothermic is a reaction where we get a peak in a downward manner, and endothermic in an upward manner. Now, the evolved gas analysis shows us that water is evolved right here. So here's the water scale here. It's a relative scale. So we have a weight loss reaction. The weight loss comes from evolution of water, and it's an endothermic reaction. Endothermic reactions usually mean that a decomposition has taken place. On further heating this material, you see that there's an exothermic reaction right here, and this one peaks at a higher temperature. An exothermic reaction, we can quantify that amount. The machine measures the total weight change in the process. So basically, we have a lot of information. The evolved gas portion will show you some water vapor evolved. Well, we know now that that reaction is dehydroxylation, expulsion of water vapor when we get up into the range of 500 degrees C, 565 degrees C or thereabouts. But at low temperature, we're going to evolve water because we're burning out carbon. And what do we get when we burn out carbon? Water vapor and carbon dioxide. At elevated temperature, we can pick up a little hydrogen fluoride and some sulfur dioxide. So the simultaneous thermal analysis of a material gives us a fingerprint of the material. A fingerprint meaning that it gives us characteristics of when reactions take place. Are there weight changes? Are there energy changes involved? And are there gases involved? It's very, very useful information. Okay, well, let's talk about clay ceramics. And clay ceramics are generally those that contain clay as a major constituent. weight percentages greater than a few percent. Clay materials are used as binders in a lot of different types of products, but and those levels can be perhaps 1 or 2 or 3%. But in the types of clay ceramics we're talking about, clay is the bulk of the composition. These ceramics are traditionally called traditional ceramics because societies in the evolution of history first made ceramics from natural clays. Now here's a representation of vitrified ceramics. Vitrified meaning held together by glass after firing. Crude glass that cements the particles together, the residual particles together within the ceramic. So if we take a section of the potassium aluminosilicate phase diagram here with mullite and silica, Professor Kingery of MIT in his first edition of Introduction to Ceramic plotted different types of ceramics. Porcelain products, the subject of next week's lesson, vitreous tile, electrical ceramics, electrical porcelains. I've plotted on here for you where bricks are. So bricks are aluminosilicate compositions. They're generally low in alumina content. They may be 12 to 15% alumina. If the bricks are made out of clay, then kaolin clay, then they can be even higher percentage up here. But nevertheless, most bricks are in this area of the phase equilibrium diagram. We're plotting this showing potassium as an ingredient because in most heavy clay ceramics, potassium is the most active alkali phase in creating melting within the ceramic. Not the only one. Sodium certainly has a part to play, but nevertheless, we've represented it like this. You'll see this diagram again next week or next class when we talk about porcelain products. Now, to further illustrate this, you can see that here's a percentage of elements, relative abundance of elements on the surface of the Earth versus the atomic number. And the rock forming elements here are present in very large percentages. So these are the elements. You see silicon, aluminum here, calcium, iron is up here, lithium, some of the alkalis, fluorine. So these elements are up here, and of course water clays, but products of decomposition of rocks. So that's the constituents of the surface of the Earth, and that's what we expect in our clay ceramics. So heavy clays are, of course, heavy clay products are made from these types of clays that we're talking about. Societies have been making these products for at least 3,000 years. If you read some history books, you would see suggestions that they're as old as 10,000 years. So people simply mined the clay from the surface of the Earth. Later on, subsurface mining became available to societies. But nevertheless, the ancient people found that they could expose these materials that had been formed into objects, fire them in furnaces, heat them to elevated temperatures, generally above red heat, which is the emission of light in a red wavelength above about 900 degrees Celsius. And when the objects were cool, they had permanence, particularly resistance to water, and especially resistance to weathering. So societies became very good at this in the Middle East and the Greek Empire. The Romans were very, very good at this, and they made products that we can see today in buildings in Rome and in Western Europe. Here's some quick facts. First of all, there's no recipe on how to make these products. Okay, There's no national standard telling you what clay you've got to use or how you've got to fire it. The standards, as you will see from this third bullet point, only deal with the properties that you're required to produce to make a good product. So people use trial and error. That's what they had available in ancient societies, learning how to make the products that they were making. They could understand the time of firing. They could judge the temperature in the kiln from the light color that was emitted from the inside of the kiln. And they knew what was required to produce a good product. The practical requirements of any clay for making a brick or a solid object are that it must have plasticity. These products are made by plastic forming, so that means that when the water was added to the clay and mixed in the clay intimately, sometimes that's called pugging in today's terminology, but nevertheless, the clay must be plastic so that you can form it into the shape that you want. The second practical requirement is the material must melt over a range of temperatures for you to be able to fire it in a kiln. If it had a discrete melting point, like a lot of metals, we really couldn't center it. We're depending on forming a certain amount of vitreous phase and controlling that amount of melted or vitreous phase by using temperature and time. And we know that if we overfire the product, then it's likely to slump. It's likely to have too much vitreous phase. There'd be too much melting. Now, I did point out that consensus standards were published on physical property requirements. I will mention this to you later in the course, but nevertheless, sometimes I'm asked, what's a good brick? And let me say that my definition of a good brick is a good brick that meets published consensus standards in a region of the world. In the United States, ASTM, American Society for Testing Materials, publishes these. There are European standards and so on, Australian standards, Canadian standards, you name it. So I always say a good brick is one that meets those standards in terms of properties that they publish or performance that they publish that a product must have. I may have my own opinion of these standards, and this will come out in the lectures, but my opinion doesn't matter because it's the consensus of smart people that establishes what a good brick is. Now, there are some differences in national standards. For example, we in the United States define freezing and thawing durability based on physical properties. In Canada, with some more extreme freezing and thawing conditions, their physical property requirements are different. In the European community, the ceramics are required to exhibit performance in a freezing and thawing test. There are some differences in national standards. And like I say, a good product is one that meets those standards. Here's some overall compositions of some brick products. If you look at the alumina and silica, the alumina content of most bricks made from clay and shale is in the range 12 to 20%. Balance is mostly silica. This is the overall silica in the composition. Silica can be present in the vitreous phase and in quartz that makes its way through the firing process. But there's always a little titanium there, some basic oxides, calcium oxide, CaO, and magnesium oxide. Iron oxide, Fe2O3, is why most bricks are red. And then you see some soda, Na2O, and potassium, K2O, present in the composition. And those are the major fluxes in the composition. So having said that, there are some differences. There's a clay called marl, which contains calcium oxide. A lot of marls are used in certain areas of Canada and in Europe to make brick products. let me say that changes some of the properties of the product when it's fired. Calcium oxide can lead to an expansion reaction on firing. We think about bricks shrinking when they are fired because they're made by vitrification sintering. And bricks made of marl shrink, but they also have some expansion when the calcium oxide reacts with the aluminum silica. And that expansion creates a little difference in pore structure, creates some fine pores. Fire clay is used to make light colored bricks in North America. And usually the fire clays contain more aluminum oxide. That's one type of product. Fire clay used in brick compositions usually gives you a yellow-brown type of color to the brick. And then there are kaolins, which are used in producing more white bricks. And the kaolin, as you can see, can contain 37% alumina. This icon is supposed to be loss on ignition right here. And so that's the weight lost when the clay is heated. Now, let me say that a lot of these clays are blended. For example, some clays and shales can be blended with fire clays to get specific colors. Some people blend kaolin and some shale to make bricks. So clays are blended usually for very specific reasons, which I'll talk about in just a minute. So we have various mineral types. Kaolinite is the basis of the mineral kaolin and also the major constituent in most shales. In the upper Midwest of the United States, we have some oolitic clays going into Canada. A different crystal structure decomposes on heating at a little different temperatures. We have marls, we have fire clays, and kaolins. So clays, of course, always have moisture content variations. They're natural materials. A lot of brick producers will extract the clay, mine the clay, and put it into stockpiles in order to try to get the moisture content to be more or less constant when it's used in manufacturing the product. In addition, the particle size of the clay can vary as you go into different depths of mining, as well as the carbon content. This is a particular problem with some shales. The oxidized clay, the lighter colored clay is near the surface of the earth, and if you go deeper, you get into blue shale, as it's typically called, which is higher carbon content. And so that can give you problems in firing to burn that carbon out. If you don't burn it out properly, you can come into certain types of problems. Of course, we talked about iron oxides. Now, there are reasons to blend clay. Usually around a brick plant, the clays are blended because one clay, it might be the most economic for you to mine, is deficient in plasticity. So you can add a second clay to it in order to increase the plasticity for forming. Another reason is to extend the firing range. Some shales melt at vitrify in a very narrow range of temperatures. So if you mix a higher melting point clay with it, like kaolin, you can extend that firing range and change the color at the same time. Clays can contain sand, of course, because they're mined from the surface of the earth. The amount of sand is important in the quality of the product. In molded brick products, sand is added. There are two ways to make bricks: by extrusion, that's lower moisture content, and by molding, either by hand or machine, usually by machine. And molding is a process of higher moisture content. So sand is added to reduce the drying shrinkage. Ceramic aggregate called grog that doesn't shrink when used is used to reduce both firing shrinkage and drying shrinkage. And then clays have these accessory minerals that you probably don't want. The main one is quartz, silica sand that we don't want. We can have pyrite, iron sulfide, limestone, calcium carbonate, mica, stones, gypsum, calcium sulfate sources, and things like that. And of course, to mention that clays are the source of fluorine emissions because fluorine is in the clay crystal structure in very small quantities. So when you heat the clay or fire the ceramic, you're going to get a fluorine emission. We'll talk about that in the last class. Now, product standards usually in products like tile will differentiate between extruded tile and pressed tile. Not for bricks. Our product standards in the United States are the same for both molded and extruded products. I've never agreed with that because they have different characteristics. But the people that make consensus standard prefer to have all bricks to be the same as an engineering material. Bricks are characterized by water absorption. The more porous the bricks are, the bricks will absorb water. And water absorption is a very easy, practical way to have a judge of the porosity of a brick. Water absorption can be done with boiling water or with cold water. With cold water, we'll get the capillary absorption. With boiling water, we'll get the total absorption. So there's a special ratio of cold to boiling water absorption called saturation coefficient. It sounds like an important property. It's just a ratio. And of course, the North American standards and ASTM for brick products are shown below. And we have a strength specification, we have a water absorption specification, and we have a saturation coefficient specification. By having a maximum saturation coefficient specification, we limit the number of fine pores that can be present in a brick. Now, in some countries, particularly the UK, color has been used an acceptance standard for bricks. Most people think well-fired bricks are darker red or blue, black in color. That's not always the case. It depends on their raw material makeup. Well, there's some things to say about firing heavy clay products. The first thing to be said is there's a large volume of material going through a kiln. Okay, so bricks as products typically stacked up on one another on kiln cars, conveyances that go through a continuous tunnel kiln. And there's large volume. And unlike many of the industries I've worked in where you understood chemistry and particle size very well, the product going into the kiln, you typically don't do that with bricks. You have intuition that tells you what it should be. You know a little bit about the raw material. There's some pre-firing testing going on. I've made an analogy of a brickmaker to the captain of a ship in a stormy sea. You're up there in the brick plant, maybe in the kiln control room. You got all these bricks flowing underneath you in the kiln, the tunnel kiln. It's like a captain on the ship. The captain on the ship knows something about the tides and the waves and the wind, but these things change all the time. And that's true in firing bricks. You have a lot of things going on with raw material variations. You've done the best job you can of perhaps stockpiling, of homogenizing the material, but a lot is going on in making a brick. Now you can say that the clay and heavy clay products is somewhere represented on the silica to alumina phase equilibrium diagram, and clay bricks are over here. I've already shown you that, and we're going to have fluxes over here in this system. when we look at that, the main flux that we become interested in is potassium. So here's the final brick composition, but in preheating the brick, somewhere amongst the fines, we'll form some high potassium content liquid phases, vitrified phases. Vitrification generally occurs here above about 780 degrees C, and it's because of the formation of glass with potassium oxide. As you continue firing the brick, the liquid composition changes a little bit, and we get to higher temperatures. Actually, in a clay brick, we'll form the second glass. The second glass is higher in alumina content. The two glasses are practically immiscible, meaning they don't mix together. And so in a fairly low fired brick, you're going to be able to detect the lower glass phase as the major glass phase that's there. And a higher fired brick composition, you're going to have the higher alumina content. The higher alumina content is more resistant to water solution. Makes the brick last for many years. The lower alumina content glass is more susceptible to water solution, and so typically clay bricks have a very small water solubility. It's due to this potassium-rich glass that's present there that's making that happen. So on heating a clay mineral, the basic things that happen are dehydroxylation. Now, you might say that's a complex word. Dehydroxylation, that means removal of hydroxyls from the clay crystal. That's typically going to happen above 500 degrees Celsius with baelinite type minerals. With illites, it can happen a little bit higher in temperature, but nevertheless, the dehydroxylation is the removal of OHs from the crystal structure of the clay. Now, hydroxyls, when the clay crystal decomposes, that's an endothermic reaction, right? It takes energy to make that crystal decompose. The hydroxyls come zinging out, but they're very chemically active and they can't survive as OHs. They'll steal some hydrogen from somewhere and form water vapor. So one of the consequences of dehydroxylation is the evolution of water vapor. Later on, mullite will form. Now, generally, we talk about the first mullite that forms as primary mullite. Next week, when we talk about porcelain products, we'll also talk about secondary mullite, mullite that is a crystal precipitates from the liquid phase that's present in firing. But in bricks, we really get concerned mostly about the primary mullite that forms. And we can see that on the differential scanning calorimeter. You'll see it right away. And then vitrification takes place. That's the melting that we just talked about, the first and perhaps second liquids that form on firing. We haven't talked about quartz yet. That's very important. Quartz that's going along for the ride. But vitrification takes some of the silica that was present in the clay and perhaps attacks some of the quartz that's present and forms the liquid phase. And we form a few percent liquid that serves as a cement. It bonds the residual particles together. These residual particles include dehydroxylated clay and quartz and other minerals that may be present. They're cemented together by the crude glass that's formed in firing. Okay, here's a dilatometer curve. Dilatometer, right? Dilation, thermal expansion of unfired clay that has sand in it. Okay, body sand is one might call it. So we're starting out from the temperature here, room temperature, and we're heating up. This temperature is given in degrees Celsius. Okay, so that is something I need to note, so I will not be as confused. And we go up here and we get up here and dehydroxylation takes place at the same time in the same general area as the quartz is going through what's called a crystallographic inversion. We go from alpha quartz, which is present at room temperature. It's in the sand that's entrained in the clay, and it expands ever so slightly on heating at 573 degrees C. That's very predictable to beta quartz, the higher temperature form of quartz. And so we have two things going on: the endothermic decomposition of the kaolin and the alpha to beta quartz transformation. Now, generally, this quartz transformation doesn't give us too many problems on heating in the kiln when we're firing the ceramic, but it certainly can give us problems on cooling. We further heat, this particular clay begins to show some evidence of incipient fusion. That's the beginning of fusion. Incipient means beginning, fusion means melting. And up here, then we begin to melt quite in earnest, and shrinkage takes place. So this is permanent shrinkage in the clay object. Okay, if we further heat, we're going to form primary mullite up here, a bit above 1,000 degrees Celsius. And that has an important effect. It slows down the shrinkage a little bit. You can notice that very slight bend in the curve there. That really becomes important in firing porcelain products. We'll talk about that next week. Now, it's important. What if we fire up to, let's say, this temperature? Okay, let's fire up to that temperature. We're getting up to a pretty good temperature here, and about 600 degrees. When we start cooling, then the material is going to go back through quartz. So it's going to shrink. And that's the shrinkage that takes us some effort to avoid in firing clay products, because it can cause cracking. So we don't rehydroxylate. The water hydroxyls don't come back into the product, at least for a long time. Okay, bricks that have been exposed to the earth for hundreds of years can rehydroxylate, but not in a short period of time. Let's say we heat up here to this temperature. What happens? We've had some shrinkage, so we're going to start cooling, and we're going to go back in this direction. Okay, when we get to the quartz inversion, we're going to have a sudden shrinkage. We're going to go down here, and sudden shrinkage, and then we're going to cool further down to room temperature. There'll be a net shrinkage here involved. Well, we know that firing results in firing shrinkage. So we know that there's going to be a net amount of shrinkage. Typically, we like to see not more than about 1.5% linear shrinkage in firing a product. The lower the better. Later on, we may talk about some products that undergo expansions as well as shrinkages. So that may influence the shape of this curve somewhere up in this region right here. But nevertheless, when you cool a ceramic that's been heated, a heavy clay ceramic, it contains free quartz, not combined quartz. Combined quartz is in the glass phase. The free quartz is the quartz granules that are present, and they're going to shrink, and they're going to cause us some difficulty. Now, here's a chemical representation of dehydroxylation. And this reaction, as it's written, would tend to say that 3 clay units, gram molecular weights of clay, will give us mullite, 3 alumina, 2 silica. That's the formula for mullite. Plus, it's going to kick out some silica, plus 6 water molecules. It's really not as simple as that, because I just showed you that dehydroxylation takes place, but you don't form mullite. Dehydroxylation above 500 degrees C, mullite above 1,000 degrees C. So what you'll find in the next class is that mullite formation is through a series of steps. Not this simple, but that's how I was taught this reaction as a sophomore, a second-year student. So here's some more information about dehydroxylation. Kaolinite's down there at about 585 degrees C. Illite's up to 750 degrees C. Montmorillonite, very plastic clays that are in a few rare cases used to make bricks, used more as binders in ceramics. Dehydroxylate up to around 700. You can see that talc and periphelite are up there a little bit higher if you have those types of minerals present. Dehydroxylation reactions are always endothermic. Okay. Iron oxidation may require significant times at elevated temperatures. We know that we have red iron oxide hematite. Fe2O3 is one possibility of oxidized iron. We have magnetite, magnetic iron oxide, Fe3O4 as a black iron oxide that can be present. So as iron progresses in oxidation, the color can go toward a red, toward a black in color. And we know that fluorine is evolved. Now, fluorine is evolved during dehydroxylation, but the body can hold on to it. The ceramic can hold on to it. After all, the ceramic is a thick section of product, and we're making bricks, and it can slowly release fluorine later on. Preheat reactions involve removing hygroscopic water. We talked about that in the drying course. Hygroscopic water is water attached to the surface. You'll recall that hydroxyls, water molecules, are polar in nature. Due to that polar nature, they have a positive side of the molecule and a negative side. And the positive side of water molecules is typically attracted to the negative outer charge cloud on a ceramic particle. Now, clay particles can have positively charged edges. I realize that. So the water molecule can turn around and be attracted to that side. But nevertheless, that water typically comes off around 250 degrees Fahrenheit, the boiling point of water. Now, we can have hydrates present, calcium sulfate hydrates or aluminum hydroxide present in raw clays, and they can give off some water vapor at elevated temperatures. There's typically a minimal volume change when these products dehydroxylate because they're present in low amounts. I said dehydroxylate when they release their hygroscopic water. Now, we haven't gotten to quartz yet, but it's important that we talk about carbon removal. And traditional carbon removal is by burnout. Okay, burnout means that we require a few hundred degrees Fahrenheit to oxidize the carbon. Typical reaction, carbon plus oxygen gives carbon monoxide or carbon dioxide, and that's what we expect when carbon oxidizes. It's not always what we get. Low temperature oxidation of carbon can produce CO that can make its way down the tunnel kill. We also can have higher density carbons that are present there, not just from the organic acids that are present in clays, but maybe from particles of coal or particles of wood that are present either inadvertently or intentionally. And these products burn by smoldering combustion. Smoldering combustion is combustion in the absence of a flame. It's like charcoal used in a grill or barbecue, where there's no flame present while the cooking is taking place, but certainly combustion is taking place, oxidation of carbon, and that takes place in ceramic products as they're being fired if they contain these higher density carbons. Reactions are exothermic. They can be diffusion controlled because oxygen must make its way into the body, the wear, in order for the oxidation to take place. The process is exothermic, and it can lead to CO emissions. It's important to burn the carbon out, or at least that was the thought in yesterday's world. Traditionally, people made bricks with what was called a clear burn. They burned all the carbon out so that the product was the same color on the inside as in the surface. Carbon burnout and dehydroxylation overlapped in temperature space, so that's what can happen. If you burn the carbon out after vitrification has taken place, we can have bloating. Okay, bloating means that we have gas molecules that are trapped within the product, and that can cause expansion due to the thermal expansion of the gases that are in those trapped bubbles. Somewhat analogous to making a pancake or wheat cake. Some people add carbonated water, club soda to those compositions to make them form bubbles and be lighter in nature. Well, that's what happens if carbon can't make its way out of the body and you have vitrification taking place. So here's one of these STA curves of a body that's pretty complex. Here's the TG curve, the green curve, and we've got here the, well, I have to look here. The H2O curve is the blue curve, showing us some evolution of water when carbon is oxidized, and of course dehydroxylation of water as the clay is heated. The CO2 in this case is in red, the red color. And you can see you get to a minimum temperature to ignite the carbon that's present, but we have several little peaks. Now, these peaks indicate to me that, in fact, we had a more complex carbon in this clay product, perhaps some residual coal particles that were there. Coal mining tailings or residues are used to make bricks. I've been in a plant in France that made bricks that didn't have to add any fuel to fire the bricks, because once they got the tunnel kiln hot using gas, then the bricks contained enough coal residue to fire themselves. Kind of a neat idea. In this particular case, we also had a carbon peak at elevated temperatures, indicating that some of the carbon didn't burn out until higher temperatures. So I hope that you can see that these types of graphs are very useful. Laboratory data is very useful for you to understand what's happening in preheat. So if you're not interested in heavy clay products and you're making a technical ceramic that contains a complex polymeric binder, you want to look at how the binder is removed. Of course, binders are removed by process complex polymers by something called depolymerization. It breaks into fragments, and you can see it leaving the ceramic body, the TG curve. They also oxidize in some cases. So you want to give the ceramic time to release these organic phases, whether they're molecules or whether they're carbon dioxide, before you have any vitrification take place. Otherwise, you can have some problems. Now we have what we call oxysalts in many of these natural clays, particularly if the clays are from areas where iron has been made from clays. Historically, we might have iron sulfides, pyrite, present. And the traditional explanation is that we have a two-step reaction of oxidizing the iron sulfide, FeS2 to FeS, and then that oxidizes again at higher temperatures. Dr. Sanders and I have decided that decomposition of FeS2 can take place in a range of temperatures, with the sulfates being oxidized at a little higher temperatures than some of the technical literature would tend to suggest. There are also some intermediates in the iron sulfide oxidation. If you don't burn all the sulfur out, then you can have problems with a defect in heavy clay products called efflorescence or staining, meaning water can penetrate the bricks in service and they can discolor. The most interesting example I ever had of that was bricks on a school in Hershey, Pennsylvania. Many of you will know that Hershey, Pennsylvania, in the United States is where Hershey bars were made, chocolate bars for the first time. And of course, they're brown in color. In a particular case, white bricks were used on the structure, and the iron sulfide was not burned out. And over a period of about a year, the water that impacted the bricks from rain dissolved the iron sulfide. It came to the surface and made a brown deposit on the bricks. Well, I thought it was kind of appropriate for Hershey, Pennsylvania, chocolate town, USA. The people that were responsible for the school were not amused at all at that. Iron sulfide can cause problems. If you have iron sulfide in the clay, you probably know it because you're going to smell the SO2 that's created in burning out the iron sulfide. You'll smell it. There's a bitter smell to this. And if you walk across the top of a kiln and iron sulfide's inside the kiln, you actually will get a taste in your mouth. So you know it. You might know it from corrosion on the fill stack of the dryer stack because it forms sulfuric acid in the dryer. So here's some example of pyrites. The pyrite oxidation, the later on second step in the oxidation. That's in a material that was freshly mined. Over time, some natural oxidation will take place in the clay, even in the clay pile. And the green line shows material that had been aged. That's a little bit different, but then again, we have more sulfate to deal with a little bit later on. So that's kind of a representation of what a lot of people deal with in manufacturing heavy clay products that contain iron sulfide. Carbonates, calcium carbonate is limestone is particularly present in some clays that are mined. So you're going to be able to see that. Here's the weight loss curve right here. The water evolution during dehydroxylation, and then we get carbonate decomposition. Well, this is the carbon dioxide that's coming out from binder burnout. Later on, we'll get decomposition of calcium carbonate. Remember that we can have other types of shapes to this curve. It's dolomitic limestone, magnesian limestone. Then, of course, we have black cores and black hearts. So that's a broken surface of a brick that's a red brick. It's red on the outside, and it's black colored on the inside. This is called the black core, and it results from the incomplete burnout of the carbon in manufacturing. And nevertheless, there's no carbon here in this core. There's no difference in the carbon content here. All the carbon's gone, but the effect of the carbon is there because the carbon created black iron oxide in the core, magnetic iron oxide. So the question is this a defect in the brick? And it's not, because it's allowed in brick standards. One problem that can develop is you can get a delamination here between the high carbon area and the red oxidized area. If we have cracks formed here, there's some delamination. In my opinion, there could be a problem with these bricks in service. Now, I'll tell you a little quick story. One time I wrote a position paper for my research supporters on black cores in clay roofing tile manufactured in the state of California in the United States. Now, the ASTM standards for clay roofing tile allow black cores. They say it's okay. They say, in fact, it's a good thing because the reduction of the iron creates a little more glass in the body, makes it stronger. That's a good thing. So I wrote a paper about black cores and sent it off to California. Well, a couple of months later, I got a call from the president's office at the university, and they say the president has received a letter saying that I've written something that has caused the citizens of the state of California to be defrauded. So I had to come up and talk to the president. Well, I had to go try to explain to the president what a black core in a ceramic is, and that it's allowed. And I don't think he ever understood that at all. He couldn't understand what a black core was. But when I told him that black cores were allowed in the standards for roofing tile in the United States, he said, "Oh, okay, everything's okay. We're not going to get sued here at the university." And he thought that was a good thing. So I got out of that difficulty by standing behind the standards. So that was kind of funny. It really happened. And what happened is the legal department of the university called me up and said, "You're going to put a disclaimer on any reports that you write from now on." I said, "Okay, no problem. Put in a disclaimer." Well, nevertheless, this brick was manufactured in the UK, and I got a call, actually an email from a guy saying, "Our brick has these cores, or does that make the brick bad?" And I had to say, well, did the brick meet national standards and the European community? UK was part of the European community when that email communication took place. And I said, if they meet the standards, they're okay. They're good bricks. So with the European Thermal Insulation Order and successive legislation, the amount of energy used in brickmaking has been reduced, and so they're more prone to see black cores in these products now because of energy restrictions trying to eliminate or reduce global warming gases. Of course, we can see gas evolution. This is by that coupled thermal analysis instrument, so we can pick up water vapor, CO2, we can pick up SO2. So we see that in firing. Here's another representation of the acid gases, including the HCl. It was picked up by the infrared spectroscopy instrument in a couple of different cases. So we do have these gases evolved in firing. In the last class, you'll find that the chlorine in heavy clay products is usually associated with the organic phase of the bricks. So chlorine, unlike fluorine, chlorine is in substitution within the clay crystal structure. Chlorine is not. It's present in the organic matter that's there. There could be salt sources in the area where the clay was extracted, like sea spray, I don't know. But nevertheless, we're going to get chlorine emissions, sulfur primarily due from the pyrite, but can be present from the fuel in the body. Now we got to talk about the quartz. Finally, we got to the quartz. So here we are. Remember, alpha quartz is stable at room temperature. On heating at 573 degrees C, we form beta quartz, and that's a little bit of an expansion reaction. Okay, so when that happens, the quartz expands. You're going to see later on that there are some other reactions with quartz. Quartz can go through a conversion to a different crystal structure altogether, forming other minerals. But right now we're just talking about that inversion of alpha to beta quartz. So we heat up the quartz. The quartz goes for a ride as an accessory mineral through the kiln. We might get a little bit of surface vitrification there. And so we're going to get about 2% expansion or thereabouts on heating. On cooling, remember that this material, the vitrified material and residual clay particles around that quartz granule solidify. At certain temperatures, they solidify where the glass solidifies once again, but the quartz hasn't gone through its beta to alpha inversion. Now it's attached to the vitrified matrix at certain points, and when it shrinks, it pulls on that vitrified matrix, and so the cooling through the quartz can cause cracking to occur, micro cracking. Well, if there's sufficient amount of cracking, we're going to reduce the strength of the product. In colonial times, in the United States, back to the 1700s and 1800s, bricks made along the coast were fired at very high temperatures because of the high quartz content, the high sand content of the clays along the coast. That required some special kilns called downdraft kilns that design was imported into the United States. But further in the inland, in these early times, they used updraft kilns because they didn't need as much temperature. So brick makers are typically going to try to limit the amount of quartz that's present in the body because they know it's going to give them cooling problems, susceptibility to cooling cracks. So here's another very direct linkage between heating and cooling rates and the quality of the ceramic. So what's going on within the ceramic as a minor component, an accessory material, makes us alter our firing schedule in order to accommodate cooling through the quartz inversion. Now there are some other forms of quartz, mainly cristobalite. Cristobalite is a different mineral altogether. Cristobalite is formed when you exceed about 1250 degrees Celsius in practical times. It says here it exceeds about 1150, but 1250 is a more practical temperature for making cristobalite. That's an entirely new crystal structure. So the quartz can be in part or in whole transformed into cristobalite. Now that can be a problem because the cristobalite itself goes through inversions, but at much lower temperature than quartz. So we can go from beta to alpha cristobalite, and that can cause cracking in the ceramic wear right as the product exits the kiln, or it can cause delayed dunning later on, years from the time when the product was made. But we usually don't see cristobalite problems in firing of heavy clay products. There is some cristobalite in beach sands, sands extracted from the sea, but generally the quartz that we see on the surface of the earth from decompositional rocks, it's there as alpha quartz, not cristobalite. Now, natural cristobalite is found in meteors, for example, things that have been heated. Well, here's part 5, the end result. So there's the exit in of the tumble kiln, making bricks, and they're looking pretty nice. They're stacked up there along the kiln car, and so we made a pretty high volume as the bricks exit the kiln before the kiln door closes. Here's a typical firing curve for heavy clay products. You've noticed that we heat pretty fast. Okay, so here's the temperature versus the hours of firing. We heat pretty fast, but we slowed down a little bit here when we got into the area of dehydroxylation. Okay, and that's to avoid what are called preheat cracks. If we heat too fast through this area right here, the water vapor and carbon oxidation, CO2, that's formed in this preheating can cause preheat cracks in the ceramics. So it's just a volume change that's causing that. Once we heat up a little more, that difficulty is gone, and we come up here to the maximum temperature in the kiln. Now in the past, maybe a generation ago, we cooled off more slowly, okay? And you're going to see that that just requires a lot more time, meaning a longer kiln. But with modern technology, brickmakers learn to apply the quick cool. So they cool very rapidly to a point at which the glass begins to solidify. They call the bricks pyroplastic, meaning they will deform easily at those high temperatures, but they get down here in this realm of, in this case, about 1500 degrees Fahrenheit, and they cool more slowly in this area right here. Sometimes we'll see them even cool more slowly as we go from beta to alpha quartz, or certainly if there was cristobalite, then they cool more slowly down in this area. So the end result in the United States is that we get cold water absorptions. They're a little different for extruded brick and shale. The molded shale were made with a lot higher moisture content, so the fired product has a lot higher ability to absorb moisture. Because it's less dense, it's going to have less compressive strength than the average brick made by extrusion. Now notice the cold water to boiled water absorption specification. The specification says that the bricks must have a maximum of 0.78, and the average brick made in the United States is right at the maximum. Okay, well that tells me that some are going to be above that maximum, and that certainly is the case. Molded bricks, because of the higher moisture content, have less finer pores, more larger pores, and their C over B is less. The initial rate of absorption, that's the rate of absorption in a very thin water bed, is a lot higher for molded shale than it is for extruded shale. And that's because of the pore characteristics of the product. Now we define freezing and thawing resistance based on this cold over boiled absorption average. Much of the rest of the world is smarter than us, and they talk about it being defined in terms of performance. Well, that's my personal opinion, not the opinion of the consensus standards that we have in North America. When you subject a fired brick to X-ray diffraction, as I've shown here, and there's the diffraction pattern, meaning the X-rays were directed in certain ways by the crystals within the fired product, and we get peaks in certain areas, and some of those peaks are due to quartz, of course. In this case, the machine identified some tridymite and some cristobalite along with mullite. The glass phase is not identified because it's amorphous, but it does give us some low angle scattering, and some of the modern instruments can quantify this amount of glass phase. If we look at a brick on a microscope, this is what we're going to see. The picture on your left is a optical microscope picture at fairly low magnification, likely about 100 diameters originally when I took this picture. And you see black spots all over the microstructure. Those are pores. So the light is coming directly down onto the surface. It's being reflected, but when it goes in a pore, it bounces around. You don't get a reflection, so we see pores. So bricks are pretty porous. I liken them to a sponge, a natural material sponge used in housekeeping, which are full of pores. Now there is a continuous phase in the brick. It's gray and white. The white is streaks of hematite, Fe2O3, so this is a red brick. The dark gray phase is the vitrified phase that contains the residual clay particles. All the clay particles don't form glass. In making a brick, they're there. We can't see them because they're so small. These clay particles are what lead to the moisture reabsorption characteristics of bricks, which causes them to expand a little bit over time. And over a long period of time, like hundreds of years, it can cause the brick to disintegrate. The more glass phase that you have here, the less porosity you have here, the more resistant the brick is going to be to disintegration. And that's why bricks in Roman structures in Western Europe, particularly where there's freezing and thawing potential, the bricks are still looking very good. The Romans knew that they needed to fire the bricks to very low water absorption, very low porosity to make them durable. Imagine that, knowing that 1,000 years ago. Here's a scanning electron microscope picture of a brick. It here shows quartz particles. The gray particles are sand particles in the brick. You can see little black pores. These little pores are mainly elongated, shaped like a slit. It tells me that this was an extruded brick, and the vitrified matrix is lighter in color because in a scanning electron microscope that's reflecting the electrons in a backward motion so that we can collect them to form the image. So there's glass and iron in this matrix. So the iron is not always very uniformly distributed. Okay, well, today, even with crude products like heavy clay products, I've tried to make a connection between phase diagrams and transient phases, the initial liquid formation and forming these products created by potassium, about the fact that we can form a couple of different glasses and firing some of these products, and they can be identified as immiscible in most of these heavy clay products. We don't naturally know that, we don't see that, but that's the deal. I've also tried to make a connection between slowing down on cooling through dehydroxylation as we evolve water vapor and have carbon dioxide being formed from binder burnout. Also tried to talk about initial vitrification and how this can be a complex situation. We want to typically not have carbon being evolved at a point at which we're forming glasses, although carbon can show its effect in black coring in the product, which we typically see a lot of in today's world as we try to minimize energy utilization and meet environmental goals. We talked a lot about quartz. As we go through quartz, we know from the low temperature alpha to the high temperature beta, and we have a little bit of an expansion, and we have vitrification. It's on cooling that quartz goes from beta to alpha. We get that at 1.5 to 2% contraction taking place, and that can cause cracking within our product. We know that if we go to very high temperatures, like above about 1250 degrees Celsius, we can form other crystalline phases from the quartz. No longer quartz, it becomes something else, so typically cristobalite as a mineral. We've seen other things that come along for the ride from naturally mined materials like iron sulfide, limestone, gypsum can be present. There's a lot of technology that we haven't talked about. I've always liked the fact that limestone was intentionally added to some bricks, limestone fines, to help in carbon burnout throughout history. What the limestone decomposes, you got CO2, and that decomposes into CO and some oxygen, and that helps in carbon burnout. So there's a lot of fun things to talk about that we haven't talked about, but I really wanted you to see that connection between laboratory instruments and what they tell us, phase diagrams, and what they tell us, thermal dilatometry, what it tells us, and how we adjust the firing temperature. So the next class, we're going to talk about porcelain. It's a more difficult product to make than heavy clay products. It's made by different processes. The bodies are typically composed of quartz, sand, brown sand called potash flint, kaolin clay. We use something to bind it together, and feldspar to create glass. And they're fired at higher temperatures, and you can see right away they're fired at temperatures that can change quartz into cristobalite. So that's going to be a neat class. I hope you've enjoyed this one, and we will get together next time for the next class.